Review chapter 1. List the elements in the set. So the squiggly brackets here, of course, represent a set. So when we write our set out, we're also going to use some squiggly brackets or something that looks kind of like squiggly brackets. X is an element in the set, and X is a counting number multiple of 2. So this set contains all counting numbers multiple of 2. So there's no negatives in this because it's, counting numbers. So we're going to simply start with 2 because 2 times 1. So 2 is a multiple there. Other multiples of 2, 2 times 2, 2 times 3, 2 times 4. Those all end up being 4, 6, 8, 10, 12, etc. And that set ... does continue on forever. But we don't have to list it forever. Let's just list a few elements in that set. So we establish the pattern, and then a ... will be enough to represent, the fact that it goes on. So it does continue forever, but that's it. So the numbers on the sides of a normal die. So our set here is going to contain any numbers that are on the side of a normal die, which a normal die goes to 6 sides. So we have side 1, a 2, a 3, a 4, a 5, a 6. And then we close that set. There's no ... here because there's no continuation. That is all the elements in the set. That is all the numbers on the side of a die. Identify the set as finite or infinite. So finite means that there's a specific number of elements there that you can physically count up to. Infinite means it would go on forever. So if you look at, example 1 that I did previously is an infinite set because it goes on forever. You can see ... continues on, never ending. So that would be infinite. Number 2 is finite because there's only 6 elements in that set. That's strictly 6 elements. There's no continuation of that or anything. So number 3 is going to be finite. It's exactly the same thing as number 2. So there are 6 elements in that set, and it stops. So it has a finite number of elements. 4, X is a prime number. So that set, just so you understand what prime, that set would be 2, 3, 5, 7, 11, 13. I'm trying to think of all the prime numbers. 17. Anyway, it's prime numbers, but there is no cap on prime numbers. That prime number list does indeed go on forever. So for that, we would call that an infinite set. So I'll just label it I. Number 5, X is a counting number multiple of 2. Well, we just did that earlier. Number 1, I mentioned already that it was infinite because it does go on forever. So I'll put an I for infinite there. Number 6, it looks kind of funny. You just go 8, 4, 2, 1, 0.5. So it looks like it's cutting in half every time. And then I got a ... here, but it does have a last element. This long decimal here is a final element. There's no ... after this. It strictly ends there, which means it has a finite number of elements. I don't necessarily know exactly how many are in this missing gap here, but this number indicates that there is an ending point. And if there's an ending point, then it can't be infinite, right? It can't go on forever if it ends. So that's finite. And then same thing in number 7, you can see 1, 3/8, 9 64ths, 27 over 5/12. I have a gap here in the middle, but I do have an end point. So this fraction here is at the very end of my set. So it doesn't go on forever. So that is just going to be finite as well. N of A. So this notation means number of elements in that set. So, and A is just representing the set. So, it's talking about this set in particular. I mean, they're both labeled A. But if I labeled this set B, then this would be number of elements in B. It's just, but this is indicating that you're kind of counting how many elements are in that set. So this set here has -5, -4, -3. There is a gap in the middle, but I can tell that it goes -2, -1, and then it does end at 0. So if I want to see the whole set listed out, it'd be -5, -4, -3, -2, -1, 0. And that has 1, 2, 3, 4, 5, 6 elements in that set. So the number of elements in A is 6. For number 9, again, -9, -8, -7. There's a gap in the middle here. but it does end at 0, so it'd be -6, -5, -4, -3, -2, -1, and then it ends at 0. So if you wanted to see the whole set listed, you can certainly write it. And now we're just counting how many elements are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So number of elements in this set is 10. So complete the blank with either an E or an E with a line through it. This indicates element or not element. Basically, this one means it's in the set, or this one means it is not in the set. So for number 10, we're looking at 8, and I'm basically wondering, is 8 in this set? And as you can see, it's right there. So yes, it is in that set. So you would label it with an E. Number 11, you're looking at number 7. Is 7 in this set? Well, based on the pattern, it looks like it's going 0, 2, 4, so it's only even numbers. 7 is an odd number, so it probably is not in that set. So I draw an E with a little line through it. Number 12, 9. As you can see, 9 is in this set. It's the very last element, so we'll say it is an element of that set. And then number 13, this is a little tricky, but we go 0, 5, 10, and all the way up to 35. So it does go by 5s, but this is -5. And since we start at 0, it doesn't seem like we're going to go into the negatives at all. We go 0, 5, 10, and we're going upwards in this set. So no, it doesn't seem like -5 will be in that set. So we'll say not an element. Number 14. So U, meaning universal set, contains all of these elements. So basically for 14, 15, and 16, that's U set that I just circled there is going to be sort of our benchmark set, the set that we're going to be basing every other problem on. So those are all the elements that I'm going to consider. 1, 2, 4, 5, A, B, C, D, E. I'm not worried about anything else that's not in that set. So I'm only worried about those elements. Complement means opposite. So look at 14, for example. We have the elements 1, 4, A, D, E in the set for number 14. Complement is everything that is not in that set relative to our universal set. So 1 is in that set, T, 4 is in that set, A is in that set, D is in that set, and E is in that set. So the complement is every other element, 2, 5, B, and C. I believe that's it. So that is the complement. We denote this as T prime, by the way. It's T with a little, I don't know, apostrophe. But yeah, T prime is what we call it. So now we'll look at 15. So S prime, that will be the complement of S. So S, let's go back and let's start from scratch. S has the element 1, it has the element 2, 4, and 5, has A, it has B, it has D, and it has E. So the only element it doesn't have is C. So the complement, S prime, is just the set C. And now we'll do one more. We'll look at R. So R prime, again, everything that's not in R. R has 5 in it. R has B in it, has D, and it has E. So the complement would be 1, 2, 4, A, and C. All right, so shade the regions. So these can be kind of tricky, but we'll do the best we can here. So we'll call this A, we'll call this B. So I'm shading A prime intersect B prime. So when you look at the arch here, that means intersect, and that means and. So you're shading regions that are essentially not all together, but the overlapping region that the two spaces would have. So A prime, and I'll see if I can't try to use colors here. Is there a way I can change the color of this pen? I'm not 100% sure. Maybe there is. Maybe there isn't. Maybe there is. All right. So A prime is everything that's outside of A. So in red, I would shade in everything that is not in A. That is all of this good stuff here, including this part that is in B as well, as everything that's not in A. That right there is A prime. Intersect B prime. So B prime, and I'll use, I guess a light blue here. B prime is everything that's not in B. So B prime would be all the space outside of B. All right, and that includes this region here that's in A as well, is not in B. So we're going to shade that in too. Now, the answer to the actual question, because if it was a union, I would stop and everything I've shaded would be done. But it's not union, it's intersection. So the only part that matters is the part that both regions are overlapped in. And the red and blue are overlapped in this region here, right? I mean, where I'm shading green, that's where the blue and the red are currently overlapped. There's no overlap here or here, right? That was all red and that was all blue. So that's not part of the intersection. The intersection is where the two shaded regions would have overlapped, which is just basically outside of it. And another way to think about this problem, as I kind of clear it up, another way to think about this is it's outside of A and it's outside of B. So the only part that's outside of A and also outside of B is essentially the rectangle part that I had just shaded a second ago, right? Outside of A and outside of B. So it's not in A and it's not in B, which means it's all of that. Number 18 is the union. Unions are easy to shade. I just mentioned that earlier. That you're shading everything outside of A and you're combining it with everything outside of B. So you don't have to really worry about, I shouldn't use black here actually, now that I think about it, because it's gonna get kind of in the way of all my other lines. Let's just shade it. What was I saying? Everything outside of A and outside of B. So you don't have to worry about intersection here. You just shade in each part, and your final shaded is your final answer. So this is everything outside of A right here. So, and now I'm also going to shade in everything that's outside of B. So outside of B, remember B is, it's kind of hard to see at this point, but B is right here. Don't forget. So I'm going to shade everything outside of that. And that's going to be basically the only part that's outside of B that isn't shaded yet is here in this A portion. Shade all that in. All right. So basically that is your answer. The only part that isn't shaded is right there in the middle. There's no shading in the small part where they overlap, but everything else is technically shaded in. So number 19, A intersect B prime. So let's draw this out. A, B. So intersect means and. So it has to be in A, and it has to not be in B. So it has to be in A. So I'm going to shade in the region inside of A. And it's not in B. So I'm not going to shade any part that gets in B. So when I'm shading A intersect B prime, this is it. It's that portion right there. It's in A, so I've shaded everything in A and outside of B at the same time. That part is in A and it's outside of B at the same time. So that's kind of my way of thinking intersection. All right, moving on. Well, that's not what I wanted. Can I go back to? Okay, there we go. I want, well, I don't know. I've ruined it, but it's okay. All right. Let A be the set 1, 2, 3, all the way 14, be a universal set with subsets B, C, and D as indicated here. Find B prime intersect C union D. So I have two sets that I'm going to find. First, let's find B prime. So I need to find B prime, and then I'm going to intersect it with C union D. So let's B prime, if B is this, remember B prime is everything that's not in that set. So that would be from the universal set A here, a 2 is not in B. A B has 1, 3, 5, and 7. So basically I'm going to include everything except for 1, 3, 5, and 7. So it'll be 2, 4, 6, 8, and then all the way up to 14. 9, 10, 11, 12, 13, 14. So that's your set B prime. It just basically is a set A, but it does not include 1, 3, 5, or 7 because those were the original elements in B. But now I need to write the set C union D. So this is the set that combines C and D together. So if you combine all the elements here in these sets, you would have the set 1, 2, 5, 6, 7, 8, just trying to put it in numerical order, 13, and 14. So now, to write my answer, B prime intersect D prime. So these are the two sets that I was interested in. Now, intersection means elements that are shared within both sets. So I'm looking for elements that are in both sets. So if I look at both of these sets, I'll notice both sets have a 2 in it. Both sets have a 6 in it. Both sets have an 8 in it. And both sets have a 13 and a 14 in it. So that is my intersection set. So the answer here is 2, 6, 8, 13, 14. Yeah. Number 21 is basically the same problem. So I hope it's okay with you. I'm just going to kind of bypass it, skip it, because you get the point. Number 22. So number 22, it's kind of like the shaded region we were dealing with earlier, but a little different. So I have the set A, and I've got the set B. So U is 52. So all the elements added up within this rectangle is 52. So we'll keep that in mind. The number of elements in A is 28. So 28 elements in A, but I'm not sure how much of that 28 is in this space versus this space, because both of those spaces are technically in A, but I'm not sure. I can't just put 28 here, because then that's assuming that there's nothing there. You know, for 28 elements to be in A, there could be 20 elements here, and there could be 8 there. That's 28 in total, but I don't know all that information just yet. I just know that 28 will eventually be the total for those. The number of elements in A intersect B. So this is the shared region between A and B. So that's this middle part 4. So I do know that there's 4 there. Now, knowing that there's 4 there, that tells me if there's 28 in A, and 4 of those 28 are right here, that 24 elements are there, because 24 with 4 makes the 28 elements in A. So I know there's 24 elements there. So I've used that information. B prime. So B prime is everything that's not in B. So there's 28 elements that are not in B. I already know 24 of them are here, right? This 24 is not in B. This 4 is in B. So I'm not really worried about that 4 right now. There's 28 elements that are not in B. 24 of them are here, which must mean the other 4 elements are within this rectangular space, right? 24 and 4 makes 28 in total, and that's a 28 in total that is not within B. All right. And the last thing, there's 52 in total. So if there's 4 in the space in the rectangle, 24 in A, 4 shared within A and B, then the difference must be how much is left here in this B portion. So if I take 52 and I subtract 24, and I subtract 4, and I subtract 4 again, Basically, I'm just taking away all of these regions that I've already counted. That would be a total of, I think it's 20. So you can check my math on that, but that should be 20, I believe. So all of these now added up should be 52. All right, I'm going to skip 23. It's very similar, but I'll do number 24 because it's a little bit more intense, I think. There are 3 circles here. We have A, we'll make it a little bigger, A, B, and C. All right. So again, U is 213. So in total, this entire space has 213 elements. A has 72 elements, but again, you don't know how much of that 72 is broken up into all these different regions within inside of A. So, but I know all of them added up would be 72. Let's jump to some information that might be useful to us. So A intersects B intersects C. So this is where all 3 regions overlap, and that's 16. So the only place that could be is right there. All 3 regions overlap is 16. So I know 16 is there. Also, not in A, not in B, and not in C. The only region that is not in A, B, or C is basically the rectangle. The rectangle is outside of everything, and this says outside of everything. Not in A, not in B, not in C is 54. So 54 is going to be our region in our rectangle. Now, this one here is kind of interesting. It's not in A, but it is in B. So we're thinking about, let me try to use a different color to emphasize this a little bit. So I have to look outside of A. So look, here's A. I'm going to look outside of A. And it's in B. So if it's outside of A and in B, could be anywhere within this space right here. Right? That's in B and not in B, in A. But also it says out not in C. So the only part that's not in A, not in C, but is in B is that region. Ooh, oh man, tried not to erase it, but I did. It's basically just this region here. So that means that region is 45. So this is 45 because that region is in B, but it's not in A and it's not in C. So that is 45. So now let's look at some of the other information we're given. A intersects C. So in A and in C is 34. So that's this little football shape here. Now I already know 16 of it belongs. I've already got 16 in there. So if it all adds up to 34, then 34 minus 16 is 18. And that's going to be the leftover space there. So now if you combine 16 and 18, that is 34 elements shared between A and C, which is what that indicated to me. A intersects B. So that's the football shaded region here that overlaps A and B. Is 31. Again, I already know 16 of them. So the remaining must be 15. And now if you combine 15 and 16, that means that shows us 31 elements between A and B. B in total has 92. So I already know 45, 15, and 16. So if I take the difference between that and 92, I'll have that last part where it joins C. So let me get my calculator. We'll test that. So 92 minus 45 minus 15 minus 16 equals 16. So that's going to be 16 here. And that totals up to 92 within B. A has 72 in it. So again, I already know 15, 16, and 18 in A. So the only region I need to find, I'll just take the difference between 72. So 72 minus 15 minus 16 minus 18 equals 23. So there's 23 elements there. And now all I have to do is figure out how much is in that C portion. So to do that, I'm going to take 213. I'm going to subtract every single other number there from it, and we'll see what's remaining. So 213 minus, we'll start with 54, then we'll do 23, 15, 16, 18, 16, and 45. And I got 26. So that means the leftover bit is 26. It goes in C. All right, moving on. Number 25. At Franklin Junior High School, 11 students take German but not French. 21 students take French but not German. And 46 students take at least one of these languages. So to figure this one out, we'll have a circle for French class and one for German class. So 11 students take German but not French. So that's right here. That's 11 students that take strictly German, and there's no overlapped region there with the French folks. 21 students take French but not German. So 21 is going to be strictly in the French section, and again, ignoring the overlapped region because it specifically said not taking German. 46 students take at least one. So that means if I combine everything within these circles, it should total up to be 46. So the question is, how many students take both French and German? How many people are here? Well, all we have to do is take the difference between the 21 and 11 from the 46 that we already have to see what's left over. Because, 21 students take strictly French, 11 students take strictly German, but there's 46 students in total. So if we take 46, subtract 11, and subtract 21, we get 14. So there are 14 students that take both. So if you combine them all now, you'll see that should be 46 students in total. So all you have to do is take the difference there. It's a little bit of subtraction. At Ridgemont High, 30 students play tennis, 6 students play tennis and golf, 8 students play golf and softball, 9 students play softball and tennis, and 4 play all 3 sports. How many play tennis only? So I'm going to have a couple circles here. Well, I guess a few circles. All right, so this will be for tennis, this will be for golf, and this will be for softball. So I'm going to start with the fact that 4 students play all 3 sports. So that's going to be the overlap region in the middle is a 4. And I'll work my way backwards. 9 students play softball and tennis. So if 4 of them already play golf as well, then 5 more play strictly softball and tennis. Because if you combine this region here, tells us the tennis and softball shared, 4 plus 5 makes that 9 in total. 8 students play golf and softball. So golf and softball is this region here. I already have 4, and 8 students played in total, so there's 4 more there. 6 students play tennis and golf. So tennis and golf is this football-shaped region. 4 students are already counted for, 6 in total, so that means there's 2 left here. And that combines to make 6 students in total. So 30 students play tennis. So the question is, how many play tennis only? So it's just going to be taking the difference. I know 2 of them play this, 4 of them play that, 5 of them play that. So if there's 30 in total, we'll take 30 and subtract the 2, subtract the 4, and subtract the 5. And that, I believe, is that's 30 minus 11, so I believe it's 19. 19 play tennis only. All right, student considers, I should say various options, I guess. He has for college. He can attend a college in Florida or Alabama. There are 3 colleges he's considering in Florida, and all of them offer 3 majors he likes. There are 2 colleges he is considering in Alabama, and one of them offers 2 majors he likes, and the other offers 4 majors he likes. An option is a state, a college, and a major. How many options does he have? So if you just draw out a tree diagram, you'll be able to count how many total extensions of that there are. So his first choice is a state. So he has 2 states he's going to choose from, Florida or Alabama. Once he's chosen a state, he's going to choose a college. So there are 3 colleges in Florida he's considering. So 1, 2, 3. 3 colleges in Florida he's considering. And there are 2 colleges he's considering in Alabama. So Alabama has 2 colleges, 1, 2. So in the colleges in Florida, all of them offer 3 majors he likes. So every one of these colleges offers 3 majors he likes. I'll call it A, B, and C. This college also offers the 3 majors he likes, A, B, and C. And then this one offers A, B, and C. Alabama, one of the schools offers 2 majors he likes. So one school offers 2 majors he likes, and the other school offers 4 majors he likes. So A, B, C, D. So how many options do you have in total? Well, I mean, all the final options are listed kind of here. So if we kind of count that up, we'll see how many there are in total. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. That'll be 10, 11, 12, 13, 14, 15. I'm just counting up basically all these letters at the end. There are 15 in total. So there are 15 different ways he could, I guess, pick a way for his future. So number 28, there are 15 ways to do task 1. And there are 28 ways to do task 2. How many ways are there in total? So basically, there's 15. I'm not going to draw all 28, but I'll make a, dot, dot, dot. Okay. So there's 15 ways here, and then there's going to be 28 ways here. I'm just going to visualize this to explain why. It's pretty simple. So I guess I can write numbers out here. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So basically, if you do the first way, choose 1, that first way, or option A or whatever, you could pair that with all 28 for option 2. And that together, that 1 with those 28 means that there's 28 ways there. But then you could take option 2, right? And you could pair that with all 28 of option for the second part. So that's another 28 options. And you do that 15 times, and you can see the answer is simply going to be 15 times 28 to figure out the total number of combinations. Whatever that number is your answer. Number 29, a shipper has 5 routes from Philadelphia to Atlanta, 3 routes from Atlanta to New Orleans, and 4 from New Orleans to Kansas City. All you have to do to find out the total number of ways is, same as the last problem, multiply. If there are 5 ways to do task 1, 3 ways to do task 2, and 4 ways to do task 3, that will give you the total number of ways. And I believe that's 60. And last one, a code consists of a letter followed by a single-digit number followed by another letter. So a letter, a number, and then a letter is our 3-digit code, or single whatever code. Letters can be repeated, so on and so forth, from the first 12 letters of the alphabet, and the numbers come from 1 through 7. So the first part of my code is a letter, and there are 12 options because it says I can choose one of the first 12 letters from the alphabet. So there's 12 options there. As far as the number goes, for the second thing, there are 7 numbers I could choose from. So there's 7 options for that. And then I choose another letter. And since I can repeat my letters, and there's 12 of them in total, that means there's 12 options again there. So 12 times 7 times 12 gets me the total number of options for my code. So whatever 12, 7, 12 is would be my answer. That's going to be it, guys. It's a long one, but I think all of these are going to be pretty long. But, I do it just to help you. I'll see you in chapter 2. Okay? Later. Good luck. Bye.